For decades, the scientific consensus held that the earliest humans arrived in Europe around 1.5 million years ago. But in 2019, researchers re-examining nearly 5,000 animal bones from a forgotten excavation in the 1960s in Romania found microscopic cut marks indicative of butchery without any stone tools or human fossils present. High-precision uranium-lead dating of associated tooth fragments established a minimum age of approximately 1.95 million years, half a million years earlier than the previous benchmark at Barranco Leon in Spain. If these traces are correctly interpreted as evidence of hominin activity, they would reshape our entire understanding of when and how humans first occupied Europe. Yet can laboratory protocols truly distinguish ancient human marks from natural damage with this level of certainty? The answers begin with the bones themselves. The Grounceanu bone collection stands at odds with the established timeline for early human presence in Europe. Until now, the earliest widely accepted evidence came from Barranco Leon in Spain, dated to about 1.4 million years ago and supported by stone tools and cut-marked bones. Grounceanu, however, offers no tools or hominin fossils. Only a set of animal bones show microscopic marks that researchers interpret as butchery. The claim rests on 20 bones, 8 of which display high-confidence cut marks, all dated to approximately 1.95 million years ago using uranium-lead analysis of tooth dentine. This pushes the possible arrival of hominins in Europe back by nearly 500,000 years. The evidence, if correct, would not only predate Barranco Leon, but also precede the Dmanisi site in Georgia, which has long anchored the story of early Eurasian dispersals at 1.8 million years ago. The Grounceanu claim relies on the ability to distinguish cut marks made by stone tools from those produced by carnivores, trampling or root etching, without the benefit of direct artifacts or skeletal remains. This scenario places extraordinary weight on the interpretation of surface modifications, and it demands rigorous protocols and quantitative methods to justify any assertion of human activity. The question is not just whether these marks are ancient, but whether they can be reliably attributed to hominins, given the absence of corroborating evidence. The scientific and historical implications are profound. If the Grounceanu marks represent genuine butchery, the map of early human migration into Europe must be redrawn. Between 1960 and 1966, Romanian paleontologists excavated the Grounceanu site in the Oltet River Valley, collecting thousands of animal bones under the constraints of the communist era. The field team recovered 4,983 vertebrate fossils, but systematic destruction of excavation notes and maps during political purges left only the physical specimens as evidence. Lacking detailed field documentation, Romanian museum curators at the Emil Racovita Institute and the Museum of Oltenia transferred the entire assemblage into climate-controlled basements for safekeeping. For over 50 years, the collection remained stored and largely unstudied, its scientific potential overlooked due to the absence of original context. In 2019, Sabrina Curran, an anthropologist at Ohio University, and Claire Terhune, a curator at the University of Arkansas, gained access to the Grounceanu fossils through collaboration with Romanian colleagues. Their approach prioritized the physical integrity of the collection, emphasizing the value of direct re-examination over reliance on lost records. The sheer number of preserved bones offered a rare opportunity to apply modern laboratory techniques to an untouched early Pleistocene assemblage. However, the lack of stratigraphic logs or field maps imposed significant constraints on reconstructing the original depositional context and precise, find locations for individual specimens. This situation made laboratory-based taphonomic analysis essential, as all inferences about ancient activity would have to rest on the observable features of the bones themselves. The rediscovery of the Grounceanu collection thus transformed a neglected archive into a focal point for testing claims about early human presence in Europe, with Curran and Terhune leading the renewed investigation. The standard scientific model for early human arrival in Europe has, for decades, centered on Dmanisi in Georgia. Fossils and stone tools from Dmanisi are reliably dated to around 1.8 million years ago, making it the benchmark for the earliest confirmed hominin presence outside Africa. This timeline has shaped the accepted narrative. Hominins first entered Eurasia through the Caucasus and then gradually spread westward. For Western Europe, the evidence has been even younger. Sites like Cima del Elefante in Spain and Kokabas in Turkey have produced remains and artifacts dating from 1.2 to 1.4 million years ago, but none approach the antiquity of Dmanisi. The mainstream view holds that sustained hominin occupation of Europe began roughly 1.5 million years ago, with populations expanding intermittently as climate and environment permitted. The list of key early Pleistocene sites is short and well-defined, with Demaniasi, Barranco Leon, and Cima del Elefante forming the backbone of the European record. Each of these sites features either hominin fossils or unmistakable stone tools, providing direct evidence of human activity. The absence of earlier, unambiguous finds has led most researchers to treat the 1.5 million year mark as a practical lower boundary for European settlement. Any claim of a significantly older presence, especially one based on indirect evidence such as cut marks on animal bones, demands extraordinary scrutiny. The scientific community relies on a strict hierarchy of evidence, placing fossils and tools above more ambiguous traces. This is why the Ground-Seanu findings, if validated, would represent a major departure from the established model and would require re-examination of how and when the first humans entered Europe. Technicians began by screening 4,524 bone specimens from the Ground-Seanu collection using a standardized macroscopic protocol. Each bone was examined under low-angled lighting to enhance surface contrast and scanned with a hand lens at 10 times magnification to detect linear modifications. Observations were logged directly into a digital tablet, recording the presence, orientation, and character of each mark. The protocol required immediate classification of every specimen into one of several bins: unmodified, naturally broken, weathered, root-etched, carnivore damaged, or candidate for anthropogenic modification. Most bones displayed only natural damage or root etching, which typically appears as sinuous, shallow grooves with irregular trajectories. Potential cut marks were defined by their straight, linear paths, often transverse to the bone's long axis, and by their distinct coloration relative to the surrounding surface. Any specimen with ambiguous or interesting marks was flagged for further analysis, while clear cases of natural damage were excluded from the candidate pool. Internal team discussions were held to resolve borderline cases, ensuring that only the most plausible cut-marked bones advanced to the next analytical phase. This initial filter sharply reduced the number of specimens requiring quantitative analysis, minimizing false positives, and focusing resources on the highest confidence candidates. The decision tree established at this stage formed the backbone of the subsequent workflow, enabling transparent documentation and reproducibility throughout the investigation. A subset of 20 bones flagged as potential cut-mark candidates advanced to quantitative testing. Each specimen underwent high-resolution optical profilometry, a laser scanning technique that captures three-dimensional surface geometry at the micron scale. This approach measures groove depth, cross-sectional shape, and edge sharpness, generating numerical profiles for every mark. Michael Pante, an external specialist with a large comparative database, conducted a blind analysis on the digital models. His algorithm compared the Ground-Seanu marks to thousands of reference samples from documented butchery, trampling, and carnivore modification. Out of the 20 candidates, 7 bones displayed groove metrics that matched the signature of stone tool-cut marks with high confidence. The remaining 13 were classified as probable or mixed, with some features overlapping natural damage ranges. The anatomical placement of the high-confidence marks corresponded to locations where muscle or tendon would be removed, strengthening the interpretation of deliberate butchery. Statistical discriminant analysis achieved over 80% accuracy in separating anthropogenic marks from natural ones based on established threshold values. This external validation provided an objective test, reducing the risk of observer bias and confirming that the selected marks met international standards for identifying early human activity. The results justified prioritizing these bones for direct dating, as only specimens with verified cut marks could anchor claims about the timing of hominin presence at Ground-Seanu. 7 dentine samples were selected from the Ground-Seanu collection for uranium-lead dating. Dentine, the mineralized tissue beneath tooth enamel, was chosen because it absorbs uranium after burial, but is less affected by later chemical changes than bone. Each sample was screened for high uranium content and minimal alteration, ensuring that the resulting dates would reflect the earliest possible burial of the fossils. The laboratory used a 193 nanometer excimer laser to ablate microscopic spots from the dentine, vaporizing material for analysis by a multi-collector mass spectrometer. Calibration relied on certified NIST 610 and NIST 612 glass standards to correct for instrument drift and mass bias. Because uranium does not always enter the fossil at the moment of death, the team applied disequilibrium corrections to account for post-burial uranium uptake and the decay of short-lived isotopes, uranium-234 and thorium-230. These corrections are essential for establishing a true minimum age rather than an artificially young result. Analytical uncertainties were quantified using a Monte Carlo simulation, which ran 50,000 virtual experiments by varying each input parameter within its error range to produce a robust probability distribution for each age estimate. The final dates represent conservative minimums, anchored by both the physical chemistry of the samples and the statistical rigor of the uncertainty analysis. This framework ensures that any claim about the timing of hominin activity at Grountianu rests on the most defensible chronological evidence available. 7 dentine samples from the Grountianu assemblage yielded uranium-lead minimum ages tightly clustered around 1.95 million years, with analytical uncertainties of plus or minus 0.18 million years. Each sample was selected for high uranium content and minimal alteration, ensuring reliable results. The uranium-lead method measures the decay of uranium isotopes into lead within the fossil's mineral matrix, providing a direct estimate for when the bone was buried. Monte Carlo simulations, running 50,000 iterations per sample, quantified the range of possible ages and demonstrated a narrow, consistent distribution across all tested specimens. This minimum age cluster matches the expected range for the late Villafranchian fauna found at the site, with biochronological estimates, based on animal species composition, also falling between 2.2 and 1.9 million years. Independent dating of nearby sites in the Oltet Valley, such as Valia Roskai, produced similar results, reinforcing the regional consistency. These results provide a robust temporal anchor for interpreting the site's taphonomic and ecological context, setting a new lower boundary for the arrival of humans on the continent. The convergence of radiometric and biochronological data establishes Grountianu as the oldest directly dated evidence for hominin activity in Europe. Stable isotope analysis of tooth enamel and dentine from Grountianu indicates a warm, seasonally variable climate around 1.95 million years ago, typical of a forest steppe mosaic at mid-latitudes. Oxygen and carbon isotope values point to alternating patches of open grassland and woodland, with sufficient rainfall to maintain riverine corridors. The faunal assemblage includes ostrich and pangolin, both thermophilic species requiring mild winters and substantial vegetation. Ostrich remains suggest open habitats with access to water, while pangolin fossils indicate dense undergrowth or wooded patches within the mosaic. Large herbivores such as early bovids and suids, along with a varied rodent population, confirm a landscape supporting both grazing and browsing animals. These ecological indicators align with habitat models for early Homo dispersers, who favored environments providing both cover and foraging opportunities. The seasonal structure of the ecosystem, with predictable dry and wet periods, would have enabled short-term exploitation by transient hominin groups without necessitating permanent settlement. The presence of thermophilic fauna at this latitude supports the plausibility of episodic human activity, even in the absence of direct archaeological evidence such as tools or habitation structures. 2 principal corridors could have enabled hominins to reach southeastern Europe by 1.95 million years ago. The first is the Caucasus route, which extends from the Levant through the southern Caspian region and into the foothills of Georgia. Dmanisi, located along this corridor, preserves direct evidence of hominins at 1.8 million years, confirming the viability of this passage. The second is the Anatolia to Balkan route, which links Western Asia to the lower Danube and Carpathian basins. Pleistocene paleogeography shows that the Anatolian Plateau and Balkan lowlands periodically offered open, traversable landscapes, especially during interglacial periods with reduced forest cover and accessible river valleys. The Grountianu site, at roughly 45 degrees north, falls within this band of potential movement, matching the latitude of other early Eurasian sites. Comparative records from the Loess Plateau in northern China, where stone artifacts dated to 2.1 million years demonstrate eastward dispersal, support the feasibility of broad, steppe-like corridors spanning Eurasia. These patterns indicate that early hominins could have moved episodically across vast distances, exploiting windows of favorable climate and habitat. The distribution of sites from Dmanisi to the Loess Plateau suggests that migration into Europe was not a single event, but part of a wider, patchy expansion across the continent and beyond. At least 49 early Pleistocene sites across Eurasia have yielded evidence attributed to hominin activity, but the record remains uneven and highly localized. The majority of these sites, including Dmanisi in Georgia and the Loess Plateau in China, are separated by vast geographic and chronological gaps. Many locations, such as Ain Boucherie in Algeria, are contested due to ambiguous associations between fossils, tools, and dating methods. Only a handful, like Dmanisi, provide both hominin remains and direct artifacts. Grountianu now joins this patchwork as the oldest directly dated European site, but its evidence, cut-marked bones without tools or fossils, reflects the broader pattern of sporadic, discontinuous traces across the continent. Objections center on the absence of stone tools or hominin fossils at Grountianu, raising the possibility that the cut marks could result from natural processes such as trampling, carnivore gnawing, or root etching. Critics point to the low frequency of cut-marked bones, just 0.18% of the assemblage, as insufficient for robust claims of human activity. The research team counters with high-resolution, three-dimensional profilometry, which measures groove depth and cross-sectional geometry to quantitatively distinguish cut marks from natural modifications. Blind analysis by an external specialist achieved over 80% accuracy in separating butchery marks from other surface damage, but some scholars remain cautious, arguing that limited sample size and potential taphonomic bias warrant further independent verification before accepting the claim. Upcoming fieldwork at La Pietras and Valea Roscai will apply drone-based LiDAR, high-precision global positioning system, and core drilling to recover stratified fossils and sediments for multi-method dating and taphonomic analysis. All protocols and raw data, including three-dimensional scans and isotope measurements, will be made publicly accessible to enable replication. The Nature Communications publication outlines these plans and credits the International Research Consortium coordinating logistics, funding, and community engagement. Decades-old museum collections now yield testable evidence that demands critical reassessment of Europe's earliest occupation. As analytic protocols improve, overlooked fossils may alter migration models and challenge entrenched assumptions about human dispersal. The Ground Cyanu findings, grounded in uranium-lead dating and quantitative cut mark analysis, remain under debate. Scientific consensus adapts, one dataset at a time. The question now is not if, but how much further back the record will be pushed.